All right, with slightly less terrible lighting, let's talk about the Curta calculator, built between 1947 and 1972, perhaps coincidentally overlapping with the period of greatest productivity growth in the history of humanity. The can is like so. These are now, the cans are rarer than Curtas actually, but oddly enough, it's a righty-loosey opening, not a lefty-loosey. And the Curta itself is almost impossibly tiny. I have fairly average sized hands for a man, and it easily fits in my hands. It's also not incredibly heavy, although there's a lot of stuff in it, 600 and so unique parts, as you can see from the illustration behind. And it's just beautifully made. Let's see if we can see this here properly. It's beautifully made. We've got is knurled texture on the base, and also on this ring up here, which can twist and lift and twist and rotate. And then on the top surface, we have the grinder lever, which can retract and come back, and then two sets of counters here, and then the clearing ring, which snaps into place like this. And then to release it, you push this microscopic pin down and push it back before you put it away. So next up, we'll learn how to do addition. Right, the Curta, like many mechanical calculators, really only has a handful of tricks, and the skill lies in knowing how to chain them together to do the useful thing, the thing that you want to do. And so what the Curta does is addition, frankly, just addition. And there are ways of doing this that you can basically do multiplication, division, and so on. You can also do subtraction, which is pretty neat. So inside there's some bits and pieces that essentially perform subtraction by doing what's called nines addition. And for more details, just check out YouTube or the internet. There's plenty of details there. But all the different features and parts in this are impossibly tiny. Like you could fit half of them under your thumbnail or fingernail without too much difficulty. All right, let's have a look at how addition works. So in order to perform addition, you need to first of all set, using the setting register here, the number you want to add. So let's say 123, 1, 2, 3. These all have a nice clean detent. You can see this worm gear drive in behind here, which allows you to slide these things up and down and twists basically a gear on the inside. And now you twist this handle at the top once to enter that number in the result register. And then the second number we want to add is, let's say 456. Oops, 456. One of the nicer things about this is if you make a mistake, you can basically undo any operation that you've done without too much difficulty. So we turn this once, and we've now added 123 to 456, and our result is 579. Not really surprised there. In order to clear this, you lift the barrel here, and then move the clearing lever all the way around. You can clear just half the registers if you want. So there's a counting register here that shows that we have performed 2 additions in the units column and 0 in the tens, hundreds, etc. places. Those come in handy when we do multiplication. So we'll just clear the calculation here, and we are back to where we started. There we are. Beautiful. All right, next up, multiplication. Subtraction. All right, to perform subtraction, first we need to enter a number into the result register. So we've got 456 here, entered there, and we want to subtract 123. So this actually works for any set of numbers. I'm just using the same numbers over and over again. And to subtract, we withdraw the barrel here and subtract. Result 333. Piece of cake. All right, let's talk about multiplication. I'm just going to do this fairly quickly. Hold on to your butts. So we want to multiply 123 and 456. 123 on the setting register here, and now we're going to perform successive addition. to calculate this. Now, if you had to turn this crank 456 times, that'd be rather boring. Fortunately, there's a shortcut. However, we'll do the sixes, the units column first. So 1, 2, 3, 4, 5, 6, and there's a 6 here in the counter register, so we know that we've done that right. Then we switch this to the tens place. 1, 2, 3, 4, 5. There's a 5 there, and switch to hundreds place. 1, 2, 3, 4. 456, 123. The result is 56,088. And these little pins here you can move around to demarcate decimal points if you're doing decimals, which we're not right now. That's multiplication, piece of cake. All right, we're going to do division this time. This is one particular algorithm for division. There are obviously other algorithms that can be employed, but this is the one we're going to use this time. So let's divide 1,234. So we'll just enter this into the result register here, and then we'll just clear the counter because we don't need that anymore. And now essentially what we're going to do is put 56 in here. We're going to divide 1,234 by 56, 56, and the way we do that is essentially by adding negative 56 to this number, multiplied by various powers of 10 until it goes to 0. And the way we count that is we switch this little switch here to negative, which decrements the counter instead of incrementing it. So we basically just do successively. We start at the millions place here, and we subtract 56 million from this number. In fact, we can put a decimal point there. Let's keep this in focus there to keep this decimal point there to keep track of what we're up to, but it doesn't really matter at this point. Like a slide rule, it helps to have some instinct for where the decimal point goes. All right, so we're doing subtraction, so we pull this core out here. We subtract 56 million, 56 there, we're down to 114. If we subtract again, we underflow, we get lots of nines, so we're going to add that back on. Now we drop down to the 100,000s place, subtract, and this is definitely underflow territory. In fact, I think we switch to at this point down to the thousands place. Subtract, oops, underflowed, go back up, down to the tens place, subtract, underflowed again, and then down to the ones or units place, subtract, and we're left with 0.00008, which is pretty damn small, and the result is 22.0357. And I don't have to check that on a calculator. That's definitely correct. All right, let's do integer powers. So we're going to take powers of 123. So we start with 123 here in the setting register, 123. And then we just multiply it by itself 123 times, unsurprisingly. 3 in the units place, 2 in the tens place, and 1 in the hundreds place. The result is 15,129. That is the square of 123. Now, obviously, I could write that down, re-enter that down here, and perform the multiplication to get the cube. But there's a pretty good way of doing it as well, which is to effectively wind this number up on this register here without losing track of what you're doing. So we'll go through to the 100,000th place here, and we'll wind, we're going to get 015129 on this register here. So that's a 1, and then go to the 4's place here, it's a 5, 1, 2, 3, 4, 5. We go to the thousands place, it's a 1, that's already there. Tens is a 2, it's already there, and the units place is a 3, and it's got to a 9. So we could have gone to the 2 and then subtracted 1. There you go. 15129, and the cube is 1,860,867, and we can perform the same trick again. So actually, we've run out of numbers here on the result on the counter register. So in order to multiply this by 123 again. What we in fact do is we enter this number here on the setting register, and then multiply by 123 again. But I'll do it anyway just for fun. So 127, 6, 8. I like calculating algorithms and methods that do not require you to memorize lots of numbers, because if you're doing this all day long, it's very easy to get muddled up towards the end of a long day. So we've got 1 million blah 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 here. We'll reset the top. There we are. And now we'll do 123. So my millions result register is a little bit clunky. Anyone happens to know how to fix that without disassembling the entire thing, be happy to know. Speculation not required. Okay, and we're up to whatever this is, 228 million and change. And in fact, I might be able to even do that again, but yeah, one starts to run out of digits. So that's how you take integer powers. Next up, square roots. All right, let's talk about square roots. Of course, one wants to do square roots on a mechanical calculator. There's at least 4 algorithms that I know of for doing this. This happens to be my favorite. Probably the easiest one is just division. You divide by an approximate to the square root and then take the average between the result and the square root, and that's pretty much accurate to a good number of places. This one is a little bit more accurate, and you can apply it recursively. It doesn't require great feats of memorization. So in any case, we'll take the square root of 1,234, and my guess for what that might be is about 35, because the square root of 1,000 is something like 33. So we'll put in 35 there on the setting register, and we're putting them actually here in the millions and 100,000s place. And the reason for that is that when we apply this operation, we're going to end up getting to use the whole of the counting register, which is where the result is going to appear. So this is fairly straightforward. Nope, I messed it up. All right, it's not too late to fix this. It does not start there. It starts over here, 35, and we switch to the millions place. Okay, I'm not crazy. Just not so practiced at this. 1, 2, 3, that's 3, and then the 5, put it in the 100,000s place there. 1, 2, 3, 4, 5. All right, 35 times 35 is 1,225, which is actually pretty close. So what we do now is we just work our way down, and we need to make this up to 1,234. But before we do that, we're going to double the setting here for reasons I will not go into, but have to do with just approximate plus error term squared, 70. All right, so we're going to add 70 to this and see what we end up with. That's much too large, so we'll subtract that again, and we'll drop to the next place. Add 1,232, it's pretty close. 1,234. Well, sorry, 1,233.4, 234.1. It's overflowed slightly, but we'll just subtract 1 here. 1,230.3. Take off another one. That's pretty close. And then we will add here till we get really close to the 0.000, 0.995, 0.002. And that's the ones place. That's as close as we're going to get. And here we have 35.1286. 35.1286 is, well, I think we already nailed it to 2 decimal places. This is almost certainly correct to the 4th decimal place. But we can test it. We can put in 35.1286 down here. $35.1286, and then we'll clear the top. That's the best bit. All right, and then we will run this multiplication again times the same number. Well, actually, I had the result there. I could have flipped this down and then run the subtraction all the way down to 0, but then that would have meant that it would make it more complicated to attain further refinement. Okay, 35.1286. So let's get going. We'll start in the millions place. 1, 2, 3. 5, 1, 2, 4, 5, 6, 7, 8, and 6, 1, 2, 3. All those clickings are very complicated interlocks that prevent you from messing stuff up. Okay, here we have 123.4.018533796. We've actually overflowed, we've lost the 1, but that's all right, we don't need the 1 at this point. And in fact, if you wanted to obtain many more digits of precision than you can fit on this register here, you can kind of truncate and then proceed with the algorithm. So actually we've overshot ever so slightly. So what we're going to do here is now double this this number here, and then we'll have to subtract a little bit, and that'll give us the correction. So 6 times 2 is 12. Carry the 1. 8 times 2 is 16, gives us 17. Carry the 1. That gives us a 5. There's a 2. This goes to 10, and this goes to 7. All right, and actually there's all kinds of fancy mechanisms in here that allow carrying when you're doing the calculations, obviously. All right, and now we are going to come back up to this, probably the 5th place. Well, let's see where we are. Let's try the 4th and see where we end up. I'm going to subtract off this. No, that's much too large. Okay. Actually, we're only expecting corrections in the 2's place, so we'll see where this ends up. 3, 3, 9, 401. 3.9401. That's closer. And then the last digit, let me just subtract off. 149704. Yeah, 97 is closer, but it's pretty much halfway in between. And so as it turns out, we're only off on the last digit, and only by a factor of about 2.5 there. So instead of 8.6, it's 83.5. That's kind of cool. All right, and next up, we're going to do cube roots. All right, we can't stop now. Let's do a cube root. Again, 1,234. That's got to be damn close to 10. 10 cubed is 1,000, obviously. So we will not waste time inputting numbers here into this register. And then, of course, as before, we drop to the sixes, or in this case, 10 to the 6 millions place, and we perform our multiplication. 10. All right, we're done. 1,000, and we'll put the decimal point in. 1,000 there. Okay, then, whoops, that's not right. That's 100. Maybe we should have picked a different number so we get less confused. All right, so 10 times 10 is 100, and now we're going to put 100 in here, and we're going to clear this once more. There's a way of doing this which is slightly more elegant, but it's confusing enough as it is, and we will once again multiply by 10 here. Okay, now we have 1,000. All right, and the decimal point is in the correct place. Now we have to not double but triple the n squared term because it's a cube, and then we perform successive addition to make up the number. So that's much too large. We're looking for 1,234. This is going to overflow as well, so we'll go down to the whatever place this is and build up to 1,230, I think. Nope, too far. 1,240, 1,210. 1,234. All right. Okay, that went exactly, which has given us 10.78, which I think is pretty damn close. But we may as well test it and find out. So we will put 10.78 here. 10.78. There we are in the setting register, and clear everything up here and start again. So go back to the sixes place. Hopefully we won't overflow this time. Let's find out what happens. 10. There's a decimal point. 2, 3, 4, 5, 6, 7, 8. 8. 10.78 times 10.78 gives us 116.2. So we'll move this decimal point into position. That one can go away. And that gives us, that tells us where the decimal point will appear in a minute. So now we need to put 116.2084 into this lower register. Yeah, let's live dangerously in terms of overflow. 4, 8, 0, 2, 6, 1, 1. And 10.78. Now we have to memorize that number or we're going to get into trouble. Yeah, 10.78. Well, hopefully I won't forget it. Clear the top ring. Go back to the millions place. 10.78. Luckily I didn't have to remember it for very long. 10.78 times this huge number here gives us, I may have made a horrible mistake. Possibly 1,252. Yes, I believe that's correct. 1,252.72 blah, blah, blah. So it's a little large. We need to multiply this number by 3 in order to proceed. So 3 4s are 12. Carry the 1. 3 8s are 24. Carry the 2. 2 3 2s are 6. 3 6s are 18. Carry the 1. 3 1s are 4. That goes to 4, and this goes to 3. And then we need to start subtracting because we overshot here a little bit. 1 2 5 2 1 2 1. All right, this is going too slowly. Let's bump it up one more digit. There we are. There we are. 413, 1234.9. Subtract some more. 123.5, 0.2, 3.9. Push this down and add 7,005, 347,876, 10.7263, which I think might be reasonably close. And this one I will check because I'm not too proud. 1 divided by 3. Okay, I'm getting, according to Google, 10.7260. So the last digit is not completely correct, but if you had infinite time, you could rerun this algorithm and you get that last digit as well.